and he will speak about skillful precipitation nowcasting using deep generative models for radar. Thank you very much.
Yeah, thank you for the introduction. Also, thank you for foregoing the good weather to attend this talk or this hour. So hopefully we'll make this a bit fun. I'm also glad that this is happening on Tuesday and not Wednesday because I don't think I could compete with the World Cup match tomorrow. So before I dive into like any details about ML models or anything else, I want to highlight that this work was a result of a collaboration with the UK Met Office. So prior to this project, I had no experience in weather prediction. I did not understand weather prediction, what are the important problems or anything else. And so it was really, really important that we work with someone who had deep domain expertise. And as an ML researcher, I'm always mildly terrified about working on a problem that we don't have expertise on and then solving something that no one cares about. So this came out in a paper that had a bunch of people on it, both on the Met Office side and the DeepMind side. And so everyone had diverse perspectives, all of which kind of ended in different parts of the paper. But as a disclaimer, this will be my own personal perspective on the problem. So it'll be kind of peculiar to that. So I'll discuss kind of what the problem statement is, the sort of baseline methods that people typically use for this particular problem and why we picked our particular approach on generative models. What I found interesting was actually the evaluation of these things. And so I talk about, typically how people measure these models and maybe some of the limitations that you have when you try to apply, deep learning or these very flexible machine learning methods for this before discussing kind of expert evaluation and arriving at a conclusion. So the next talk will be about climate prediction. We're and that's at one extreme end of how you're making projections, 100 years in advance. This is looking at something way nearer in the future. So sort of up to 2 hours ahead, precipitation nowcasting. What may be a little bit different than a traditional weather prediction problem is we both want high resolution in space and in time. So each of these pixels in the radar represents a 1 kilometer by 1 kilometer box that hopefully represents precipitation at any particular point. And we want to make predictions kind of every 5 minutes. And so this is very different than like a typical approach that would be used. But this might not only be useful to you, this is also useful for the Met Office for things that may not be apparent at first glance. So expert meteorologists use this to issue flood warnings in particular places. This is issued for like guidance in terms of like air traffic control, say at like Heathrow or Gatwick. There's a lot of emergency response situations beyond flooding. And then actually there's like a person at Wimbledon when the tennis tournament happens that tells you when to open and close the roof. And they apparently rely on predictions like this. So I want to, I guess, say why this is an important problem and why don't you use like a standard method? So a standard method is basically like a big fluid simulation, and it uses a simplified version of Navier-Stokes called the primitive equations. So that's not necessarily that interesting for this talk, but it is this very interesting model that's been developed, in the past few decades that predicts kind of everything over the years. So precipitation, wind speed, temperature. And so one would ask, why not use this thing? Why would we think about ML models? So one of the issues that happens with the reality of using this weather prediction method is that both it's much coarser in space and time. So typically you'll issue predictions hourly, and you might and the resolution of the actual predictions itself might be 10 to 20 kilometers. But there's also this separate effect of data assimilation. So you're going to get sparse observations of what's happening on the Earth. And what you want to do is get a full atmospheric state from this. And so this is part of like this data preparation side. What happens when you assimilate this and then you roll this forward in time, the first 8 hours typically is not great. And then the next sort of from 8 hours to 2 weeks, pretty good predictions. And so this is kind of like this very narrow area, both at coarse resolution and in precipitation, that these type of methods would work and would be useful. So what is interesting about this problem is not only is it interesting in the Met Office, I think it raises some specific issues and important statistical questions that maybe we don't think about that much in traditional or like in vogue AI research. So making sure that the predictions are spatially consistent across multiple spatial and temporal scales is something that is very, very important. The ability to capture rare events. So like flooding events don't happen that often, but you want to make sure that when those things happen, your model is actually able to make those predictions. And actually, like, you might want to even bias it toward trading off kind of near-term performance on low precipitation to something that is much heavier precipitation. We also want to account for uncertainty, which still happens at, you know, the sub 2 hour scale. And then we also want to make sure that not only do we improve scores on traditional metrics, so like improve forecast quality, we want to ensure that we can make better decisions from these predictions itself. And this is typically called forecast value. And so I'll kind of go over what people have typically done in the past, both on like the physics side and then early ML models, and maybe where the gaps are in which we try to improve upon this method. So first thing to note is kind of what this precipitation data looks like compared to standard machine learning data sets. People might want to know like how big this is relative to something like MNIST, which is a 28 by 28 digit. So you can see this on the bottom left-hand corner in comparison to the size of the radar. And then even something that's like larger scales, such as ImageNet, which might be a 128 by 128 or 256 by 256 image, you know, occupies this right corner. And so when you look at these radar fields, this is much, much bigger, and you want to ensure spatial consistency. So when we first got this data, it was kind of terrifying, but it also made us work harder to make sure that we've satisfied the desiderata that the Met Office wanted. So a typical approach might do something like advection. So I'm going to look at it from like a computer vision point of view, but there is definitely a physics interpretation. And the basic idea is you're going to take two frames of radar input, so one at kind of current time, the last one from previous time, and then using an optical flow model, predict an advection field. And then what you'll do with the advection field is extrapolate this over a period of time. And so this has a very good inductive bias of what we think rain might look like. So if we think of a rain cloud moving from point A to point B, an advection model is actually quite good. What it's not good for is a convective initiation or thunderstorm. So rain that might pop up de novo from the radar itself, and those typically are heavier precipitation. But I like kind of going over this approach because not only do we say kind of what the physics approach is, I'll kind of talk about in this next slide what happens when we neuralize this approach and try to improve upon the advection model. So the details of, I guess, this particular neural network is not hugely interesting, but it does a couple nice things. So this is an optical flow model called PWCNet. And basically what it does is it extracts features sort of at the current time and the previous time step, and then calculates these multi-scale features. So if we're thinking about spatial consistency across multiple scales, this does a pretty smart job. And then it looks at the course's resolution, does a cost voluming, so think about like cross correlation, and then from that estimates a course advection. It moves the previous time closer to the current time, and then kind of does this at, I guess, increasing resolution. So what's interesting about this is if you apply this PWCNet, which has a lot of these inductive biases, and compare it to the ground truth, you'll see this smearing effect that happens at the edges, at the boundaries. And this is something that's physically inconsistent, but weirdly will score well. And I think this will be a theme of a lot of models going forward. Another model that I think a lot of people have looked at and used in various applications and also applied to precipitation nowcasting is a UNet. And it has really a lot of nice architectural properties that look quite great. So to kind of set this up, you might have 4 frames of radar input of like the last 20 minutes of what's happened. And you have these multiple layers of convolutions. So you'll do 3 convolutions at the current resolution, downsample by a factor of 2, and then do the same thing, so on and so forth. And then you'll also have similar upsampling layers that not only look at information at a coarser resolution, but also information that's at the same resolution, but earlier on in the processing. As an architecture, this works quite well and is in a number of different scenarios. In this particular case, a couple models that people have looked at are regressions. So at the output, you'll have some pixel prediction of what the rain is at a particular moment, and you'll compare that against the ground truth, and you might use something like mean squared error. Or you could turn this into a classification problem in which you bin the individual pixels to say like no rain, light rain 0 to 0.5 millimeters per hour, medium rain, medium heavy. And you'll make a prediction, and this is one example. And you can see that it does have a little bit of advection, but it also blurs over time. So this scores well on a particular metric that I'll go over in a little bit. But what I really want to dive into is why it does this blurring, and is this going to be a problem when we create our own models? So as a slight, oh, yes, question.
I'm just wondering, the unit processes every image one at a time, or does it?
Oh yeah, so this is stacked over channels. So yeah, so it'll make a stack over channels, and then it will have a full resolution image, and then it'll be sort of like 18 frames in the future. So it kind of, yeah, every one input of 20 minutes, and then one output of the next 90 minutes. And so when I talk about scoring well, I'm going to talk about this particular metric called critical success index. But do people know what intersection over union is as a metric? So it doesn't, yeah, I could go over this quickly. So the way people typically measure these nowcasting systems is to take your ground truth and take your prediction and then set a target threshold. So let's say 1 millimeter per hour of rain. And then you binarize go to both of the ground truth and then your prediction. So everything above 1 millimeter per hour is a 1, everything below 1 millimeter per hour is a 0, and then you see how much it intersects over the union, and that gives you your score. One of the issues with this particular type of metric is that you might have different types of problems in your model, and the different types of problems might make you think that, you know, one sort of prediction is better than the other, whereas if you might give this to a meteorologist, they might say the opposite. So in this particular case, what CSI will give you in this kind of, yeah, sort of toy example is, if this is your target or your ground truth label of rain, and then this is your prediction, you know, if there's a lot of overlap and then there's not a lot of false positives, you'll get sort of very excellent CSI. But if you wanted to make sure that you had something that's positive and non-zero, you might want to predict rain everywhere. And so that doesn't give you like these very sharp forecasts. And then kind of most perversely, say your model predicts something that's just slightly away from the actual ground truth, but is close in shape to your rainfall estimate. This will give you 0 CSI. And so there's ways of mitigating this problem, but this is broadly known as kind of like the double counting. Yeah, the double counting penalty. And so this sort of blurring kind of comes from this meta optimization of looking at only a few metrics and then optimizing for that. But I want to dig a little bit deeper into why this specifically happens when these models were applied to nowcasting. And so one of the things that was not touched upon is kind of what happens at the loss function. And we have to be really careful about these objectives of using mean squared error classification if the data has some underlying stochasticity. So there might be some what are poor conditional independence assumptions. For those in the audience that are unfamiliar, I'm hoping that this example will give you a little bit more of kind of what this means. So I think one way of sort of diagnosing these problems is trying to understand what is the implied probabilistic model for the regression and classification models and what might be missing. So if you look at regression, and this is kind of your probability with some parameters, and then x of t is your prediction given your past. This is the, if you think of like regression as like a linear Gaussian model, this is a product over time, height and width of, I guess, like ground truth given your prediction. But this factorizes into your probability at a particular pixel at a particular point in time, given your past. And it's a product, conditioned on the past, a product of particular pixels. And in classification, you can kind of do the same sort of decomposition. But the decomposition itself implies something of what we thought about the model. So because these things are decomposed conditioned on the past as kind of the product of pixels, we've implied a conditional independence assumption, which is given an input, two predicted grid cells or pixels are independent. So what might this mean? And what I like to do is like, I don't know, there's going to be a modest amount of audience interaction with this and in setting up this game. And so what I'm going to have us do is, instead of having a neural network make a prediction, I'm going to have you make a prediction. And I'm going to give you two different options. So option A is I'm going to just give you information about the past. And all I want you to do is make a prediction of what's going to happen at this orange dot here. Option 2 is I will give you both the past and then information that's around the orange dot. So say this white dot here. So how many people want to use just the information about the past to make a prediction about the orange dot? Show of hands. Okay. How about the opposite? Okay, yes. This is very, very good, right? So we've assumed that there is some information at neighboring points that aren't necessarily encoded in the past. And so what we're saying is that this conditional independence assumption is probably not true. So whatever, like this is kind of a cooked up example. So what really might this mean in kind of real world scenarios? And for this, I kind of give kind of like a thought experiment. So I'm not a physicist, and so this is maybe my best attempt at one, but I think it kind of brings into the fore the particular issues in terms of making predictions. And so I have this rain cloud. It is pouring a ton of rain. It is running at 30 millimeters per hour, and it goes in one of two directions. And so it can go west at 60 kilometers an hour with probability 0.5, or it can go east at 60 kilometers an hour with probability 0.5. And then you have city W, city west here, and then city east here. So if I knew that in 30 minutes it's raining in city W, what can you tell me about the probability of rain in city east? 0, exactly. So the posterior, right, at 30 minutes says there's no rain in city east. But if we looked at the regression model, it says that raining at both places 15 millimeters per hour. And the classification, it says with probability 0.5 that it's raining at 30 millimeters per hour. Obviously, this is a cooked up example. We're doing prediction, but what I'm using in this particular example is information from the future. But, and then weirdly, you get kind of good CSI values. So if you got 0.5 with these heavy precipitation, a lot of people would say this is not close to solve, but a really, really good and fundamental advance. But why don't we think about like questions that we care about and what we want out of our models and whether they do a correct job. So what is, I guess, like given our example, what is the probability of it raining in both cities simultaneously in 30 minutes? Yeah, 0, right? Because it either moves one direction or the other. So the truth is 0. The regression model says with probability 0.1, it rains at both places. Classification model says with probability 0.25, so 0.5 squared, it rains at both cities simultaneously. So what is the probability of no rain over the next hour? Yeah, okay. So 0.5, right? So it either moves in one direction or the other. So yeah, with probability 0.5, this is, yeah, the correct answer. And then regression says no, 0% probability. And then a classification, if you're making a prediction every 5 minutes, you know, it's sort of 0.5 to the 8. So like very close to 0. And then this is like the catastrophic rain condition that the Met Office worries about. So the probability of rain in city east over the next hour, that's also 0.5. But regression model says 0 because it's averaging out these effects, and the classification model essentially 0. So this is one problem that you'll see is like you really care about these compound events. But if you're making pixel-wise predictions, you have to be very, very careful that you're answering the questions people care about. And so the forecast quality, the scores on metrics were quite strong, but the ability to make decisions based on the actual predictions is quite poor. So we want to make sure that we have both of these. And so we want to, sort of pump the brakes and sort of in a certain style of machine learning research that says, well, let's try to optimize for a metric and then kind of pray everything else works out. So this is kind of hopefully some motivation for why we might use a generative model. And so, I've belabored the point of what these baseline models do, which are these discriminative models that sort of give in the past do pixel-wise prediction. Instead, what we want is, because a lot of what are desiderata and the questions that we care about are these compound events, we want a generative model. So given the input, sample a realization, where a realization is how rainfall might evolve. And so like the major question is how to model this particular aspect. Question?
Sure, I understand what's the difference. Like if you do pixel prediction, is it also a realization of what happens in the future?
It is, but it's a pretty bad one.
But what's the difference?
I mean, I guess that's kind of what the thought experiment gives you, which is, okay, so the thought experiment gives you, if you're making these compound events and you have this conditional independence assumption, then, right, like you make incorrect predictions about things that you care about.
Sorry,
Yeah.
I understand. The question is not why is it better, but like why is it different at all? Like what's the difference? Isn't pixel prediction is exactly the same as
No, right, because we assume that so each realization enforces like temporal and spatial temporal consistency, right? Like the object that we care about is not what is the prediction kind of like of pixels like independent of each other, right? Like, so like on the face of it, right, like you're doing kind of like a H by W by T prediction, but the distribution you're sampling from is quite a bit different. So the generative model that we care about, we want to ensure the spatial temporal consistency, whereas for the other models, it's good for, if it's going to rain in a particular point in time, that's fine. But if you're having these other models, then yeah, losing that structure ends up being quite important. Yeah, so what we want is, a generative model of what might happen in the future. Of course, the question is like, how do you model it? So in, I guess, like numerical weather predictions, so these big fluid models, the way uncertainty is characterized is you'll take an initial state and you'll sample kind of n members of the future, where n like at like a weather bureau like ECMWF or the Met Office might be around 50. And so from these sample realizations, you're going to calculate the relevant probabilities of the questions that you care about. Of course, there's kind of many generative models that one can use at the particular point in time. Like that we looked at this research, we thought GANs were like a pretty good fit for what we were trying to do here. So this is, again, like another toy slide of what GANs are. So for image generation, the idea is you'll sample from some noise distribution, and then you'll have some neural network known as a generator that, given some piece of noise, will sample like an image like, I don't know, this iris setter. We might want a more conditioning. So this is an unconditional setting that gives you no control over what the generator gives you, but we might want to include other information. So we can include this Y variable, which is categorical, that says I want to sample a butterfly or a dog, and then include both of this information and then generate a butterfly. And then GANs are sort of so named because the type of training they do is a little bit different than some of the others, which is the generator samples from, I guess, this implicit distribution. And then we have the real data, and then we have a separate neural network that tries to identify whether the data came from the generator or from the real distribution. And then the generator tries to create things that look more and more like the real data distribution. And so well, our generator we're going to get from our GANs, but obviously we've talked about conditional image models, but we care about realizations of, I guess, like video. So we're going to use models sort of inspired by Big GAN, which is a large scale, or a GAN for large scale image synthesis, and then DVD GAN, which does this for video. So Big GAN is basically this conditional generative model of images that we've used before. And then DVD GAN, we feed it sort of both a latent and our input of the past, and we're going to sample completions of particular videos. And so we're essentially treating this radar as a video prediction problem and then seeing how well this does. So the conceptual diagram of this is fairly similar to DVD GAN. So we have our radar generator, which is our neural network here, our context, which is the past 20 frames of input, and then our data set, which is these observations here. And similar to DVD GAN, we have two discriminators. So a temporal discriminator that is a 3D ConvNet that ensures spatio-temporal consistency, a spatial discriminator that looks at each frame of the output and then ensures kind of spatial consistency and stabilizes training. If you train with only these two discriminators, it will give you something, the model will give you something that is very realistic, but also not based in reality. So we include sort of like this grid cell regularization term that takes the mean of our sample outputs here and then compares this to our ground truth here. And then we have this weighted distribution that caps the precipitation rate at like mid-20s. So if we did a squared error here, you can think of this as like a squared energy distance, which is a proper scoring rule. When we tried this with our data, some of the data itself has spurious, spurious values like 1,000 millimeters of rain. So training was a little bit, a little bit unstable. So we have this more as like a regularization term rather than an actual loss that is like a proper, strictly proper scoring rule. And the generator itself kind of architecturally tries to adhere to the principles that I outlined kind of in slide 2. So we have these latents that account for the uncertainty that we really care about. And then we have this multi-scale architecture. So given our previous frames of input, we have similar to kind of one side of the UNet, 4 different convolutional layers followed by downsampling layers. So we'll have convolutions here, downsample, convolutions and downsample, so on and so forth. And this provides an initial state for a convgru, which is like a type of recurrent neural net, which takes information kind of at a coarser resolution than the previous time step. And so we roll this forward kind of 1 frame at a time. And so we give this past 20 minutes of context, and then it gives us a nowcast over the next 90 minutes. And so this is kind of one particular example. So one thing that we didn't talk about is how we handled rare events. And how we do this is actually in our training data. So broadly speaking, what we do is we take crops of 256 by 256 because kind of that's the max size that we could fit on a GPU or TPU within GPU or TPU memory. And then we'll do a random sampling, but our sampling is actually biased. So somewhat surprising to me, 94% of pixels in the UK data are 0 rain, which doesn't necessarily correspond with my experience in London. But you do, so you'll have a lot of frames that have no rain at all. And so we rebalance the training set. So we have kind of like a more uniform but not uniform distribution of precipitation, both kind of very light and heavier. And then one last thing is because we've trained on crops and want to generate on large scale, on the full radar field, we want to make sure that everything is fully convolutional. So when we fit in the full radar frame, we have spatial temporally consistent outputs. And so with the various convolutions, this is totally fine, but the latent itself usually is not necessarily the case. So we introduced a fully convolutional latent layer, so that allows us to do this sort of spatial temporal consistency question.
Just real quick, how many temporal slices are you working on in the model? I many time frames does it see at any time?
Yeah, so it's last four radar frames, so 20, and every 5 minutes, so last 20 minutes.
Then I'll put the next step or the next 90 minutes?
The next 90 minutes. Yeah. So good question. So each time step of the recurrent net gives you one frame of output, and so it does this 18 times to get you the next 90 minutes. Yes.
And just building up on this with the temporal resolution, what's the rationale? Maybe you mentioned it actually, but what's the rationale about using 20 minutes to predict 90?
So this is basically an experimental thing that we tried. So we tried including fewer input frames, longer input frames. This is kind of the sweet spot that worked. So I have unfortunately, I have like no intellectually interesting reason why this was the case. But yeah, with a lot of things, especially in this area of work, it's just experimental, and this is kind of what we tried.
But from what you're saying, it sounds like using 20 minutes to predict 90 is better than using 90 minutes to predict the next 20.
Yeah. So I mean, like a lot of this information is fairly local. And so like if you look at the last 90 minutes, you'll have a lot of precipitation that evolves somewhere else. And so probably that information is not only not necessarily useful, like functionally, like it might just be noise. And so having a few radar frames of input like is actually going to be quite useful. If you had, say, something like a full atmospheric state, so not just precipitation, but everything else, you might be able to get away with only what you care about at the particular atmospheric state, maybe one frame in the past. But because you don't have all of that data, actually having a little bit of input context helps a little bit, or helps. Yeah, so that's 256 by 256 during training. So 256 by 256 pixels. And then during evaluation, we feed in the full radar frame. So that's 1536 by 1280 pixels. Yes.
So the 256 by 256, is that for the context or that for the prediction as well?
It's for both.
You didn't try to predict like a smaller thing using a larger context?
We did. It was about the same. Yeah. So one thing actually that's kind of interesting is if you think of things moving off screen, one would expect that at the boundaries, especially from like west to east, you have no information of what precipitation is going to come. And so one would expect that if you just crop this in sort of the centermost prediction, then you have the information at your input that gives you what you would plausibly expect to happen at the output. So we tried a bunch of this. We tried kind of center cropping. We had crops that decreased over time. If it made a difference, it was a couple tenths of a percent. And that, so it doesn't really matter that much. So I'll talk about kind of how well this does and kind of what the limits of quantitative verification is. So I am including both our model, which I call DGMR, Deep Generative Models of Radar, and then a couple other kind of, at the time, like well-established deep learning models, and then PySteps, which is like a physics-based advection model that does some perturbations of both an advection field and perturbations of the pixels to give you some level of stochasticity. So if you look at like all of these neural network models and you look at CSI, they kind of all look the same, and they all kind of beat PySteps by some significant margin. But they do this actually by very different mechanisms. And so it's worth digging into kind of a couple other another metric to see why might this be the case. And so, right, like one that we've talked about is blurring. But this doesn't measure blurring, but we can look at kind of like the spectral properties of this. And so these are called these radially averaged power spectral density plots. And so on the x-axis, we have kind of wavelengths that tell us kind of like at coarse and finer scales, what and then our y-axis is the power. So what is the power at any particular scale? And what we ideally want is our observations, which are in this dash black here. We want the power of our predictions to be at the same power as our observations itself. And so one way that you can diagnose blurring is if you see decreasing power over time. And so with the UNet model trained on regression, you can see at kind of higher and higher wavelengths where the power starts to decrease. And so this suggests increasing blurring over time. There's this other weird effect, which is this tail effect, which I'll show in the next slide, of this high frequency noise. And so that you can see this if you sample from a classification model. So the only kind of two models that kind of match the power spectral density are the physics type advection model PySteps and DGMR. So one of the standard things one does in kind of like weather papers is look at an interpret comparison study. So you'll take like an interesting meteorological event and then compare predictions themselves. And so the chief operational forecaster at the Met Office gave us this particular example. And he thought it was meteorologically interesting because there are these small like convective or thunderstorm cells that evolve over time. And they're actually very, very difficult to predict. So if you have something like PySteps, you'll see that there are convective cells, but it misses where exactly it is. And you'll also see that there's rain kind of at the edge of this radar, but there's no prediction there. So it predicts kind of broadly that they're convective cells, but they're A, too big, and B, the other shape of the rain is incorrect. If we use deterministic outputs like UNet, you'll see this progressive blurring, and you'll see no convective cells. And then this is the high frequency noise that I've discussed. So if you're doing pixel-wise classification output and you're sampling from this, yeah, you'll see these things are progressively blurrier. You'll maybe see something where broadly there might be convective cells, but you can't see the actual cells themselves. And then our method, you can see, you know, like up to 90 minutes or 60 minutes that these things are, I guess, like the operational forecaster told us that these things were actually predicted well and much better than kind of previous generation models. Annoyingly, like when you look at all the standard metrics, all of these methods score kind of similarly, even on this study. So what we did was we asked expert meteorologists in the Met Office who would use these things to do to issue guidance, which one they preferred. And this is their first choice rank. And so our method, you know, scored quite well. I think what's interesting is PySteps, which actually scored more poorly than some of these other other neural network models, was actually people preferred PySteps prediction to some of these neural network models because it kept the shape and things that are like physically consistent. So this tells us that there's salient properties of a nowcast that typical metrics don't incorporate. And this is an active area of research, but you know, we wanted to measure these things not with standard tools, but with something that allowed us to say like, this might actually be useful in the real world. And so we went to expert evaluation. And so we conducted what we think is sort of the first test of this, which is an expert evaluation of what a good or useful nowcast is. And so 56 Met Office meteorologists plus 20 that were in an initial like testing phase of the model participated in this experiment. And so hugely indebted because they had like actual full-time jobs beyond this. And so they did spend some time taking time out of their day to evaluate this. The other nice thing about this is they don't care about ML. They do not care about fancy techniques. They almost don't really care about things that are like physically inspired. Like what they care about is, do these things capture the properties that I care about in a prediction, and can I issue guidance from it? And so it's really nice to have people that aren't wedded to one approach or the other and will tell you that your stuff is good or your stuff is kind of awful. And then from these 56 meteorologists that participated in this, we took 10 and we asked them a lot more questions of why they preferred kind of one set of predictions over another. And how this worked is we had kind of like this online tool that we, cobbled together over, I guess, like COVID. And we took predictions from 3 models, kind of like a deep learning model, axial attention, our model, and then pi steps. And a randomized selection of cases was also given to us by the operational forecaster. So he wanted a battery of tests at medium rain, so above 5 millimeters per hour, heavy rain above 10 millimeters per hour, and then like 3 meteorologically interesting events. So we took kind of random 10 cases from about 2,000 from 5 millimeters and 10 millimeters. And the meteorologists were shown kind of what is the full frame of context at time 0, and then what area that they're looking at. What happened over the next 30, 60, and 90 minutes. So the ground truth of what happened, and then a randomized prediction, the randomized order of predictions from these 3 models. And then they were asked to make a forced choice ranking. So preferred, second most preferred, and least preferred. And then some people gave us notes of why they preferred one over another. And so this is not that interesting. It kind of says the same thing as the intercomparison study, that our model people vastly preferred. And again, like what I find interesting is even a traditional method like pi steps, again, like was outpreferred kind of 2.5 or 3 to 1 over other types of deep learning systems. So this is a first choice ranking, but if you look at pairwise rankings, this is also, pretty consistent. And then in phase 2, we asked 10 participants to go through their interviews where we asked them to sort of analyze and describe the decisions made. We used the recent case walkthrough method. And so there's kind of happens in 3 sweeps per meteorologist. So they ask, so we go over kind of like a recall of task and the rankings. And then in sweep 2, kind of like base level decisions of why they cared about this. And then 3, kind of check it for mistakes in the decision-making process. And I think what's more interesting than like maybe the numbers itself is actually like what the meteorologists cared that were interesting. So this one did not mind if the predictions themselves were had intensities that were less than the ground truth, as long as the spatial consistency was correct, because one can assume from sort of the current frame of input and what might evolve, kind of what the bands of intensity could be. This one liked things slightly realistic, even if it moved things slightly out of place, because meteorologists have a lot of domain knowledge in this, and so if you're giving it to a human evaluator, they can take this and issue guidance from it. But that's actually not true of all forecasters. So you can have lower resolution and unrealistic shapes, but you have to make sure that the shape is like preserved correctly. And so again, like this is desiderata that you might want to care about when designing your own type of model. And then this one wanted to make sure that temporal consistency was quite important. And then I don't know, like this one said nice things about the model, but it's actually like not super informative, so I can skip that. And so I think this is like the first and maybe what I hope to be more of these type of evaluations, not only to improve the model itself, but to like also take this human evaluation and then create new metrics such that we don't have to take 60 plus people, have them go through some training and spend a few hours of a day, like every time we try to like tweak the model or improve it. So I'm hugely indebted to this. I learned a lot from it. And I think I'm really quite hoping that when we decide to like have ML systems and have evaluation, we should make sure that we understand the task at hand and make sure that we have like a closer, I guess, like marriage of these two things. Yeah.
This evaluation was not compared to CFD models, what they used before the full dynamics model.
Yeah, so in the full dynamics model, basically in the first kind of like 2 to 8 hours, the predictions aren't good at all. And actually for precipitation, the models like aren't good at prediction. And actually, like it's even worse than that. So there's a step which is called reanalysis, which is you're going to look at kind of some historical data in the past, and you're going to look at some sparse observations of the Earth. And what you're trying to do is infer what the atmospheric state is at that time, given sort of your sparse observations from the current time, time in the past, and time in the future. And it's actually pretty well known that the inference of this full atmospheric state for prediction is actually quite wrong. So the physics model itself kind of has limited utility in general, and definitely has limited utility in like a nowcasting scenario. But it is that is a very good question.
Yes, so from the geologist's point of view, it was the model was like more useful.
Yeah, so we asked. Yeah, so we asked that. Yeah, so I guess I maybe glossed over this, but the specific question that we asked was, given the observations at 30, 60, and 90 minutes, which model is the most accurate, and then which model is the most accurate and gave you the most utility. So utility is like a very specific term around forecast values, so the ability to make better decisions. So that was the prompt under which people were, making their forced choice ranking.
Are there some cases in which the physical model actually performs better to rare events?
Yeah, so especially if you're looking at kind of other types of modalities, like if you're looking at temperature, for instance, like the ability to predict heat droughts or droughts or like heat waves is quite good. If you're looking at things like tropical cyclones, like hurricanes, those models, weren't that good 10 years ago, but have gotten a lot better in the past 10 years. Yeah, so we've looked at a few of them, and it seemed like this was quite a bit better. But like a lot of it, there's actually like a lot of detail that's interesting, which is when is your initialization time happen? So if you initialize at the same time as like our model, actually the first 8 hours, the predictions like aren't that good. And so like you could just say like, fine, it beats it at that. You could move the initialization time back until you got model spin up, and that will perform a little bit better. But you're also not like including current state. And then like the third issue is that in general, a lot of the model outputs that are stored hourly. And so it's like a little bit of a different use case. So you could probably run a simulator every 5 minutes, but that would be like a research system. And like, we just like didn't get HPC time for that. Any other questions? Oh, yes.
Yeah, just one question.
Yeah.
The beginning start that's using metric like textual grading or something like that. We to judge the quality of construction. So you choose to use generative model inside.
Yeah.
But doing this, you will try to optimize some loss in which you still compare fixed ways.
Yeah, so I will say, okay, so our battery of tests, like we use around 22 metrics. So like I kind of glossed over some of the other ones because they say different things, but like I don't think it's, again, like intellectually interesting. Yeah, if you wanted to like sort of belabor the point, like all this stuff is in the paper. So when we did model optimization, this actually happened in like a few different stages. So we ended up with generative models because we actually tried kind of similar things to what other papers did in the past. And then we would meet with like 1 or 2 Met Office meteorologists, and they would be like, this model is terrible. And so we would be like, okay, that's great. And then we'd go back and then try to update things. And then there's sort of this back and forth. What we learned kind of over time is we moved away from CSI to like looking at it sort of broadly. And then, I don't know, like there were essentially at some point, like there were a few of us that trained models, and then we made sure that the CSI was not awful. And then we just looked at videos, and we were like, ended up becoming very good at looking at videos, which I don't know if is, like a really like useful and wide bearing skill. But that, so this is why like I think that maybe sometimes a lot of machine learning research is on like creating fancier models, but there's like comparatively less on like how do you do proper evaluation, especially in these areas. And the other point, which I guess maybe worth talking about now, is a lot of the metrics that are used, especially in weather prediction, assume a physics model. And so you assume that you assume things for free, like physical consistency, certain conservation laws. All of these things are baked into the model. And so like, right, like even though you have a battery of tests, the battery are assume that you have something physics-based. And the metrics that you use are typically statistical. And now we've moved from a physics model to a statistical model, and we evaluate them using statistical metrics, and kind of unsurprisingly, we do well. But there's not the converse. Like we don't necessarily have physics-based metrics to say like how things are consistent. Again, this problem is, in some ways kind of niche. And in other ways, like, again, like since we don't have a full atmospheric state, like the ability to like capture conservation laws is kind of like meaningless. And so, yeah, if I had to say something which is a little bit different than like the crowd, like, I don't know, doing better measurement, like in a lot of ways might be more useful to the community than doing better models. I think there should be both, but I think like, yeah, evaluation is a bit of an area that people don't get into that I think more people should. Yes.
Maybe building on the last question, I think the nice thing that generative losses have is that they're not pixel distances. I'm not familiar with the DVD GAN model. Is there any pixel distance element in the loss reconstruction errors or something like that, or is it purely adversarial?
So in the original DVD GAN, it's purely adversarial. In like our formulation, we did have this regularization, which was included sort of like location accuracy. But you don't want to rely on that, right? Like based on a model class. You can imagine others like VAEs, for example, that, yeah, have, right, like at its output, like mean squared error. And we actually had a model that was a quite good VAE. It was just that like the power spectrum at like the lowest, or yeah, I guess like the lowest wavelength. So like the highest frequency had slightly less power than the DVD GAN. So it's kind of depending on what the desiderata are in terms of like how much, I guess, like sharpness you would have at these, very small scales. You might want to choose one over the other. Yeah, I mean, I also think that like, yeah, if you're having things that a lot of times like you don't necessarily want to regress on the metric that you have, because that might give you like a model that doesn't have, that doesn't perform well. So like the standard one is like in image models, like you could regress on like inception score or FID, but then if you sample from it, it looks nothing like real images. Yes.
Did you show the ground truth future to the discriminator?
Yeah, so what is given to it is both the 20 frames of input and then the output. So it's like the entire trajectory. So you're given the trajectory of the, I guess, observations, and then we stick the input and then our predictions. And then those are kind of like the examples from the two sets that are given to the discriminator. Yes.
First of all, I would like to congratulate you for this thinking about filling sparsity and chase with generative models. That's why it's inspiring. And my question is regarding the validation you conducted for your model.
Yeah.
I was wondering either you evaluate your model in outside the geographical area of interest as you trained on?
Yeah, so great question. So we have the UK, we had the US, and those are kind of mid-latitude regions. We tried to get data from other places because like, right, like these are relatively well-off countries, but the method's general. It was actually quite difficult to try to find data. So that started to change. So I think the Indian Meteorological Department is trying to open source data. And so I think that's kind of one aspect. The second aspect is, do these models transfer across regions? The short answer is I'm somewhat skeptical, because the radar sites themselves, the radars themselves are very specific. And like between the UK and the US, the type of radar is very, very different. So in the UK, there's things like dual polarization, which I guess essentially like has more accurate estimates of heavy precipitation. 1 kilometer. Yeah. And then kind of the US one has a nominal temporal it's single polarization, and has a nominal temporal resolution of 2 minutes, but for each radar site, they have an asymmetric volume scan every 10 to 15 minutes. And so they're not synchronized. And so you'll see these effects where one radar site will update, and then this one will stay static, and then the other one will move. And so like there's like this weird inchworming effect. So if there were if like the radar were, I guess, like uniform or like the same across countries, then one can imagine that there might be some amount of transfer. But I think like that's skeptical. I'm skeptical about it. And then even if I did it and I thought would be correct, or even if I thought it would work, I just don't think we have enough evaluation to be like, I would be confident in having that prediction.
Also, from my personal experience, the cross-geographical validation is very complicated.
Yeah.
Using the same remote sensing sources. And if you are interested, that's why we present one of the approaches.
Oh, nice. Okay.
One of the global products for 22 years of data.
Okay.
At 500 meter resolution of the whole planet.
Oh, nice.
Giving data that you can make, that you might, I don't know, might be interested in.
Yeah. So I'd be super interested in that. I'm definitely gonna stuff by your poster. Yeah, I guess I'm starting to go over out of time. Yeah, I mean, I guess like there's always conclusion slides, but yeah, I think I've sort of belabored the general story. So here's kind of like the new information that might be useful. So there's a collab, and there's kind of our model that you can download and use. Yeah, so it's in this particular GitHub repo. Yeah, so try it out. Yeah, see where it does well. I think what's more interesting is like see where there might be gaps. It would be really nice if people kind of build on this and make things better. I think like, especially in, I guess like this work, it is very multidisciplinary. So I expect kind of good ideas to come from all places. Yeah, and so that's kind of the end for me. Thank you very much.
Okay, thank you very much. Maybe we can have one last question, and after we move forward to the next person. Is there any question left? There is one question left.
Is the data like heavy hit? Because I'm thinking there must be lots of rare events in this kind of data. And if that's the case, would that be relevant for the training? Because I would imagine for like GANs, you are transforming from a light field distribution to a heavy field one. Would that cause some instability when making predictions?
Yeah, so when we resampled the data, we actually did not find this as much. I mean, like it's also hard to diagnose like stability in GANs. Like I guess there's two things, right? Like there might be like a catastrophic training step, in which case everything fails like in GANs, and then there's kind of it kind of doesn't learn as well, but you also don't have like loss functions that move down, right? Because of this this essentially like this two-player game, like your loss stays flat for a very long time, and that tells you nothing about the quality of the generator. We did not find instability issues because of this, but that was kind of, but we didn't go looking for it, right? So, yeah.
Okay.
Okay, thank you very much.